My name is Matt Parker and I love mathematics, but I think you should do maths just because it's fun and it's interesting. But the fine people at the Further Maths Support Program insist that the maths people learn at secondary school can be used in their future careers. And they've challenged me to visit some people at their places of work who are going to prove me wrong. So I've taken it quite seriously. I've got a selection of textbooks with various bits of A-level maths. I'm going to visit someone at work and I'm going to check if what they do is in here somewhere. I'm here at Framestore, a visual effects company. There's an Academy Award in the foyer, for crying out loud. I mean, there's an Emmy over there, and I've been told to report downstairs. So I've ended up in a cinema in the basement of Framestore, and I'm joined by Eugenie.
Oh.
So I've been told you use maths in your career. So I guess what is your job? What do you do here?
Okay, I'm a CG supervisor, which stands for computer graphics.
Right.
So I've worked on 4 films in the Harry Potter franchise.
Oh.
I've done lots of superheroes. That's Batman, Superman, Iron Man, and quite recently I worked on Interstellar.
Oh, there you are. Okay, I have some follow-on questions in a moment about if the fifth dimension is love, but we'll get to those at a later point. Okay, and so I have a sneaking suspicion that in the software, undoubtedly, there's going to be some mathematics going on.
Yep.
But I want to know, do you actually have to do that maths yourself? So.
Yeah, to an extent you certainly do. I mean, you can press some buttons in order.
Yep.
But the problem is that very often we'll be doing something that's slightly off the map or slightly unusual in terms of how it uses the software to achieve a certain effect. So an example that that I was asked to do once was, we want there to be fire, but for stylistic reasons we want the fire to look more curly, more spirally.
More curly fire.
So at that point, I had to go in and look at the field itself, which is a vector field, a 3-dimensional vector field, and then how are we going to manipulate those vectors to make sure that we get more spirally shapes inside the simulation.
And so you're actually using probably the curl property of what's going on in the vector field.
Absolutely, we're measuring the curl and exaggerating it.
And do you use, I mean, vectors, is that a thing you use a lot of?
We certainly do, because vectors describe where in your computer-generated environment, you'll have all of your things, all of your spaceships and your aliens will be made up of points. Those points have a position in space, which is defined by a vector, and they have a velocity, which is defined by a vector, even possibly acceleration and so on.
Okay, so let me just grab, I've got some textbooks. Let's go with Maths for Dummies.
Yep.
Because I know they've got vectors in here. Okay, here we go. I've got cross products and I've got dot products. So you would say these would be occurring in your program whenever you're doing anything with vectors?
Absolutely, and people working in this industry will be expected to know what dot products and cross products are.
All right, so it's not just a case of I hit the button that says dot product in this program. You've got to understand what's going on. Now, do you actually have can you show us an example of the kind of programs you use and what you're doing with those?
Okay, absolutely. I can show you some of the software we use.
Right.
So here I have a piece of software, 3D software, where I've got an orange ball and I've got a blue
rectangle prism thing, right?
Cuboid, and this is all in 3D, as you can see.
Okay, you can drag it around.
Dragging it around. So what I've done here is I would like this blue cuboid to be water.
Right.
Now, I can go and animate the orange ball myself, which will give us something like this.
Oh, so you've rendered out the ball moving around.
Exactly.
And so what did you do? Did you have to choose a path for the ball?
Yeah, exactly.
And then it just follows around.
Exactly.
Okay.
In fact, in this case, this was a sort of sine wave function that I did as an expression. So, so this is a ball moving around.
Yep.
And then what I can then ask the computer to do is to make this into water.
Oh my goodness.
So each of these points, there's just over 250,000 points in here.
So each of those little dots, each little like bit of water, there's about 250,000 of those.
Exactly. So I could have gone in and animated them all myself. I just would have been here forever.
Yep.
So what I've done is to equip the computer, to program the computer with the equations that govern how water moves. And those are called the Navier-Stokes equations.
I've heard of them.
I wouldn't say you need to know any equations sort of, you know, from memory, to be able to solve them from memory, but to understand what the software is doing is fundamental to be able to control it.
Now I know that the kinds of ordinary differential equations and things that people do in A-level are quite well behaved. But they can be very difficult to solve.
That's right.
What's your bit of software actually doing? Because it's obviously solving them over and over again for all these different particles. How's it doing that?
That's right. I mean, it uses a numerical method. So one of the things you learn in A-level is how to take a complex function or set of equations and solve them in a way that's efficient.
Yep.
And that doesn't explode.
By explode, you don't want things racing off to infinity. If anything diverges dramatically.
Absolutely. It is quite possible to run a simulation where all of your points end up just scattered around heading off to infinity, and it doesn't look anything like water at all.
So actually it's quite handy to have a passing knowledge of things that converge and diverge and how you solve things numerically.
Definitely.
And the equations that are going on under the skin. So you could, naively, you could just load up that software, hit some buttons and hope for the best?
You could. The trouble you get into is when you have to change something for one reason or another. Perhaps it's not going fast enough, or perhaps you're not getting the effect you want, and as soon as you change it, if you don't know what you're doing, you could end up with the sim going unstable.
And so if you wanted to, could you dig down into some of the algorithms it's using and start messing with them yourself?
Yes, you absolutely could. You can write your own solvers, you can create your own solvers in many different ways, your own simulation engines, and it's something that we tend to do on some films, will be to write a simulation, a piece of simulation software specifically for a film.
Custom solver just for a problem in this particular film.
Exactly.
And you've got another one here that you've loaded up for.
That's right. This is just a rigid body dynamic solve. This we'd use sometimes for things like dominoes, but more often things like a building that's being destroyed in a sort of large tentpole disaster movie.
Right.
You would see buildings coming down, and we would be using this, which is rather than a fluid solver, this is a rigid body dynamics.
You split the building up into a bunch of solid chunks, and then you pull one out or you break it somehow and watch everything else.
That's right.
So you need to know all your equations of gravity and motion and everything else to make that.
Yeah, absolutely. I mean, if the client will come back and say something like, the scale feels wrong, it doesn't feel big enough, it doesn't feel the right size, then you need to know, what do I need to change about the forces that's going to change that?
To change the way it looks in terms of its movement. So you've got to have an understanding of what's happening there.
Definitely.
Okay. If someone wanted to get into visual effects now, what are you looking for in the people you're hiring?
Well, I'd say that a background in maths, or physics, computer science can be a huge, huge help.
Right.
It's great to have a technical background, but we're also looking for people who are very creative. Now, maybe that means that you're very artistic, you like to paint, or maybe you like to build things. Anyone who wants to create something is going to have the right kind of mind for this job.
Okay, so you need to have some maths and science foundation, but you need to have a bit of creative flair and curiosity on top of that.
Absolutely. I mean, I think to have one foot in each of sort of artistry and the technical world makes you an ideal fit.
Perfect. Okay, so computer-generated effects are obviously used a lot in films.
Yeah.
But if people like this but don't want to necessarily work in the movie industry, what else can they do?
There's so many ways in which computer graphics are part of the world now. I mean, there's feature film visual effects. There's also visual effects in TV and in commercials.
I guess TV advertisements are full of visual effects.
Absolutely, but then there's also other things like, for example, scientific visualizations, data visualizations. There's the games industry. In fact, as it happens, I've moved out of film recently. I'm doing something different with. I'll show it to you.
Really? How?
Yeah.
Oh, okay. How are we going to get there?
Oh, we'll use visual effects.
Okay, that was one of the more ridiculous transitions I've been involved in my life, and we're at Thorpe Park.
Yes.
You can't just take me on some rides and I'll forget about the maths.
Oh no, this is all about maths.
Really?
Yeah, there's maths all the way through.
Yeah, okay, but you do visual effects in films?
Yes.
How does that tie in to a theme park?
Oh, well, there's loads of overlap. There's lots of rides now that have some kind of computer-generated content that you'll watch, maybe during the ride.
Oh, right, so like a ride's got like a story or a narrative or something, and
Exactly.
you see little bits of video while you're queuing up.
Or there's a simulator, you've got wobbly seats in front of it, something like that.
Okay, so you've moved from film to theme park.
That's right, I'm building roller coasters.
Of course.
This is the Swan. Okay. It's a modern take on a classic chain pull roller coaster.
And you're going to explain the maths of this. Eugenie, how is this mathematical?
Well, when you're designing a ride, you've got how your ride moves in space.
Right.
You differentiate that position with respect to time. You get velocity. We differentiate that with respect to time, you get acceleration. Now, in accordance with Newton's second law of motion, acceleration is in proportion to force on an object.
Right.
Which means it tells you how extreme the ride feels.
Ah, so you know the position because you've got the kind of shape of the ride.
That's right.
And then if you differentiate that, you get the velocity we're travelling at. And do you have to take into account which way up we are at any given point in time?
That's right, because that might give you a zero gravity experience.
So right now, what kind of forces are we experiencing?
Well, when we go down in the troughs, we're experiencing extreme forces, much higher than gravity. We call that your G-force.
Rightio. And so what kind of G-force is this? I believe it's about 4.5 G. That feels reasonable.
That's right, this one goes up to about 4.5, and in some places 0.
And you can do all of that through differentiating our position on the track.
That's right, it all comes down to calculus and an understanding of the maths behind speed and acceleration.
That is the quickest maths lesson I've done in my life. To be honest, derivatives are right through C1 through all the C's, and further maths is just...
Here we
wow,
are.
they've actually got differentiating functions.
That's right. So here we're looking at different types of functions, how to differentiate them.
And so this is exactly what you would be doing when you're calculating the various forces, accelerations for people on the roller coaster.
Exactly that. We use exactly this kind of maths to figure out what you'll be experiencing when the ride goes at this speed.
Okay, you've completely convinced me that both special effects in films and roller coasters, it's all mathematics from A-level.
It's all A-level maths.
Thanks very much.
Thank you.
So there you are, the vectors, differential equations, derivatives you learn at school. There is a point to them because one day you might use them to entertain other people, both with films and, of course, theme park rides, as it turns out. So there you go. I'm now totally not just going to spend the rest of the day here at Thorpe Park going on all the rides for free.